Um, 205, 216, Signals of Systems. This lecture is number 22. The section is 450, and today is Sunday, 24th of March. Time is 10 o'clock in the morning, and the schedule is until 12, but I'm going to try to make it shorter than this. Last time we talked about the Fourier series. So the topic of last time was Fourier series. Okay, specifically we are considering only periodic signals. So we're gonna let x be a periodic signal, and we are gonna assume that the fundamental period of x is t0. T0 is the fundamental period. So once we know the fundamental period, we can find the angular frequency, and angular frequencies are usually denoted by omega 0, and the unit of omega 0 is in radians per second, and the angular frequency is defined as 2 pi over t0. So once we know t0, we could find omega 0, and from this equation we know that if we multiply omega 0 with the period, the result will be 2 pi. And it turns out that we can represent x by an infinite series, and the infinite series is unfortunately in complex exponential functions. So xt could be represented as a constant ck, okay, multiplied by the complex exponential function e to the jk omega 0 t. The t here is the variable, everything else is a constant. So for example, j refers to square root of -1, which is the imaginary number. K is an index, is a summation index, and omega 0 is the angular frequency of x. Now, this by Euler's, you will use it a lot. So Euler formula, we have e to the j theta equal to cosine theta plus j sine theta. So you could use Euler's identity to convert this into trigonometric sums, where theta here is jk omega 0 t. That's theta, right? Now ck is a complex number. It is a constant depending on the index k, but ck doesn't depend on t, right? It depends only on the index k. Now to find ck, this is the integral to find ck. To find ck, we have to integrate the product of x with another complex exponential e to the minus jk omega 0 t. Now, these two functions are different, alright? One has a positive exponent, the other has a negative exponent. So you have to take that into account and don't make a mistake. And we multiply this complex exponential with the signal x, and once we got the product, we're going to integrate it. Alright, this integration is over one period. This means that the integral is over one period of x. You could start the integration anywhere, but you have to end it one period later, right? Now, once you have the integral, so once you have the value of the integral, you divide it by the period, and you're gonna get ck. Generally, ck will be a complex number, so generally ck is a complex number. Now, there's a situation where ck is a real number, right? Specifically, if xk is an even number, then ck will be a real number without any imaginary part. On the other hand, if xt is an odd signal, then ck will not have a real part, will only be an imaginary number. So let me write that down. So if xt is an even function, ck will be a real number. If xt is an odd function, is an odd signal, then ck will be an imaginary number. But in general, ck will have both the real and the imaginary parts. That's in general. Okay. Now, if k is 0, well, k is an index. Okay, k could be any integer, negative integer, 0 or positive integer. But in the case where k is 0, and that is c0, then the integral reduces to this, because e to the 0 is 1, right? When k is 0, e to the 0 is 1. So the integral is just integration of x over one period. And we know that this is just the average value of x. So c0 is just the average of x. The rest is not. Only c0 is the average of x. Okay. Now we can show that this is called the complex exponential form. Now we can show that the complex exponential form written here using Euler's identity could also be expressed in a cosine form, and that cosine form is this. Now c0 here, okay, c0 here is the same as c0 here, which is the average of x, and the summation here you have to take into account. You have to notice that the index here in the cosine form starts from 1. So in the index is only positive number. Now the complex exponential changes into cosine. The frequency of the cosine is k omega 0. Okay, and the amplitude of the cosine is twice the magnitude of ck. So you have to be careful here. This is the magnitude of ck. It is not ck. It is the magnitude of a complex number. So for example, if c1 is 3 plus j4, then the magnitude of c1 will be 5. Okay, and the phase of this is the phase of ck. So the phase of ck here, in this case, in this example, will be the arctangent of 4/3. And the arctangent of 4/3 is 53 degrees. This is C1, sorry. This is an example. Okay, so after you've got after you've got CK, all right, if you want to represent the signal X in a cosine form, you find the magnitude CK multiplied by 2, and that's going to be the amplitude of the cosine at frequency k omega 0, and you have to add phase CK to the phase of the cosine as the phase of cosine. All right, so and don't forget that this cosine summation starts from 1, whereas in the complex exponential form, it could go to minus infinity. we can also break this down using trigonometric form into the summation between cosine and sine here, and this form is called the trigonometric form, and you could go from here to here quite easily using cosine a plus b equal to cosine a cosine b minus sine a sine b. Now we use this formula to go from here to there. So using this formula, you see that AK, which is AK is the amplitude of cosine part is equal to 2 ck cosine of the cosine of the face of ck. So that is this, and the sine here is this guy, that is bk. So we got that, and this is in a trigonometric form. So in other words, given a periodic signal, we can represent it in three forms. First, the complex exponential form. Okay, to represent it in the complex exponential form, you could simply find ck using this integral. Now, once you found ck, you can use the ck to write x in either the cosine form or the trigonometric form. All right. Okay, so these three forms are called the Fourier series of x. Now, let's consider the cosine form. So I've unfolded this summation into this. Okay, so this summation is under the notation of sigma, right? So I've unfolded by plugging in k equal to 1, 2, 3, 4. So I got this, right? Now, I'm going to plot. Now, you see, this is a signal at frequency omega 0. This is a signal at frequency 2 omega 0. So I'm going to write this. This is frequency omega 0. This is the signal at frequency 2 omega 0. And this is the frequency 0. And this is a 3 omega 0. And this is at 4 omega 0, and so on. So I'm going to plot the amplitude of each frequency starting with 0, which is the frequency 0. So I'm going to plot. So if I got ck, right, I could do that. So I'm going to plot C0 here. Okay, suppose C0 is right here. Now this is at frequency 0. Now at frequency omega 0, okay, I'm going to plot 2C1, whatever it is. All right, whatever it is, I'm going to plot it. So this is 2C1. Let's say that 2C1 is right here. This is C0. And this is omega 2. This is frequency 2 omega 0. So 2 omega 0 has the amplitude of 2C2. So I'm going to plot it right here. Let's say that 2C2 is here. And this is 3 omega 0. The amplitude of 3 omega 0, this frequency is 2C3. So I'm going to plot it here. C3, and so on. Let's do another one. 4 omega 0. And so on. Now, This graph tells us the amplitude of each of the frequencies. Okay, and the frequencies are omega 0 apart. You see, the space here is omega 0, the space here is omega 0. So in other words, the signal X, the components, okay, I'm sorry, the signal X has a lot of components. Each component is at each frequency, right? For example, if xt has the frequency of omega 0, so you can plot this is the average of x, this is the main component. To z1, this is the second component, which is at twice the frequency of x. This is the 3 times the frequency of x, this is the 4 times the frequency of x. There are no components in between, okay? Components of x are only at certain frequencies, the multiple of the fundamental frequency of x. And this graph is called the magnitude spectrum of x. Okay, so we call this graph the magnitude spectrum. Of xt. In other words, we plot the amplitude of the cosine at each frequency. Okay, so you have to find ck first, right, to be able to plot this. Also, we need to use the phase information at each frequency. So I'm gonna plot the phase. Now we have omega 0, 2 omega 0, 3 omega 0, 4 omega 0. Whatever the phase is, I'm gonna plot it. So for example, C0 is negative. That means that the phase is pi here. Just an example. This is the phase of C0. Okay, and phase of C1 here. This is the phase of C1, and this is the phase of C2. The phase of C3, depending on the value of C. Okay, and this is the phase of C4. Let's say it's 0, and so on. And this graph is called the phase spectrum of xt. Okay. Now both of these plots are called the spectrum of x. It tells you if you are given these two graphs, then you can write down the Fourier series of x. And once you know the Fourier series of x, you can know the signal x. Okay? All right. Now let's do another example. Now we're gonna find the Fourier series of this signal. Okay, this signal is called the triangular wave signal. Okay, this triangular wave signal This is a triangular wave signal. So let's write down the mathematical expression for x. So from the graph we have xt. So let's consider only one period. So the one period here, I'm gonna start at minus t0 over 2 until t0 over 2. So that is one period. So this is one period. You can start at 0, but if you start at 1 0, you have to end at t0. But I'm not going to do that. I'm going to start at this time until this time. So from that, so there are two subintervals. The first subinterval, which is the left one, all right, over this subinterval, x has a slope of a negative slope, and that slope is equal to x0 over t0 over 2, and the interception is at 0. So the equation for x in the negative interval is minus 2 t0 over x0. Now this goes when t is minus t0 over 2 to 0. Okay, it is this guy. All right, and in the positive interval, the slope is 1. I'm sorry, the slope is positive. The width is t0 over 2, and the height is x0. So you divide the height by the width, and you're gonna get to t0 over x0. Now this goes from 0 to t0 over 2. Okay, so we have to integrate. We integrate to find ck. We integrate this function. Let's call it g. G is, which is one period of the signal x that we want to find the Fourier series. To find the Fourier series, we need to find ck. Okay, so let's find ck. Now, first we should find c0. So c0 is the average of x. And to find the average of x, it's easy. Look at the x, right? X is symmetry about x0 over 2. That's easy to see. So the average of x is x0 over 2, and that's going to be exactly the value of c0. So that is x0 over 2. You don't have to do integration because that's pretty obvious to see, right? Now, ck though is not so obvious. Now to find ck, we need to integrate gt over, so that is 1 over t0, okay, and that is t0 x of t e to the minus j k omega 0 t dt. So that is 1 over t0 integration from minus t0 over 2 until 0, and we have to plug in x as this one. So it is minus 2 t0 over x0. Now, I forgot t here. I also t here. All right, and then t e to the minus j k omega 0 t dt. And then plus integration from 0 to t0 over 2, and then this guy, okay, to t0 over x0 t e to the minus j k omega 0 t dt. Now I'm gonna pull these two factor out, so I will have 2 2 divided by x0. I think I got them the other way around. Sorry, I think I should have 2 x0 over t0. Sorry, it's the other way around. 2 x0 over t0. Yeah, sorry about that. So 2 x0 over t0. 2 x0 over t0. Okay, so this should be 2 x0 over t0 squared, and the inside is integration from 0 to t0 over 2 t e to the minus j k omega 0 t dt, and minus integration from minus t0 over 2 from 0 minus t0 over 2 to 0 e to the te to the minus j k omega 0 t dt. Now we need to evaluate this integral, which we can do using the by-parts integration. Now consider integral x e to the ax dx is equal to x over a. Now this is to find this integration, we used by-parts integration. So we define it as dv, and we call this u. So this means that v is equal to 1 over a e to the ax. Okay, so this integration is equal to uv, which is x e to the ax over a minus integrate v du. So 1 over a e to the ax dx, and that is x e to the ax over a minus e to the ax over a squared. Okay, so we use this formula and we plug in x as t and then a as minus jk omega 0. So the integration, the above integral, turns out to be 2x0 over t0 squared, and the inside the parenthesis is minus t over j k omega 0 and plus actually we have e to the minus j k omega 0 t, and then minus 1 over minus j k omega 0 squared e to the minus j k omega 0 t. That's one thing. That's for this one. Now the other is for this one. So minus minus t over j k omega 0, and then minus 1 over j k omega 0 squared. Sorry, we don't have enough space, so I need another page to write it down. Let me copy it and put it down here. Okay. Oh, right. But the first term, the boundary conditions for the first term is from t equal to 0 to t0 over 2. And for the second term is from t equal to minus t0 over 2 to 0. Okay. Let's see. Let's check if I did it correctly. A is minus j k omega 0. So the first term is here. That corresponds to this one. Okay, and the second minus here, and a squared is here, e right here. So that is the first one, and the second one is exactly the same. So but I have to put a minus sign here. That is this minus sign, and the inside is just the same as this one. All right, but then the boundary conditions for either one of them are not the same. So we have here. Now I have to plug in the boundary conditions. Okay, here t0 over 2, so I plug in here. So I have 2 x0 over t0 squared, and then minus t0 over 2 over jk omega 0 e to the minus jk omega 0 t0 over 2. And now j squared is minus 1, so minus times minus is plus, so I have plus 1 over k squared omega 0 squared, and the exponential term is minus j k omega 0 t0 over 2. Okay, and as for this t equal to 0, this will go away, but this thing will be 1. So I have to subtract by 1 over k squared omega 0 squared. Now I've taken care of this one. Now I have to take care of this one. And when t equal to 0, this will go away. So I'm left with this one, right? Negative times negative is positive. Okay, but we have negative here from j squared. So I'm going to have minus 1 over k squared omega 0 squared. And the last one is this guy. So I have to plug in t equal to minus t0 over 2. So this one will be positive, but I have minus here, so I have minus t0 over 2 over j k omega 0, and then e to the j k omega 0 t0 over 2. Let me see if I did it correctly. And the last one is this one. So minus times minus is plus, right? And then, but then I have j squared, so I have to be minus 1 over k squared omega 0 squared e to the j k omega 0 t0 over 2 here. Now let me see. Is there anything that is not correct? Yeah, I have t0 over 2 minus t minus goes here, so minus t0 over 2 here. That's okay. I have minus sign here, right? From this minus, and this is a squared. So j squared is minus 1. Minus times minus is plus. So k squared omega 0 squared. Okay. And then I have to subtract this one. This is plus already, so I have to minus, subtract it, negative sign, and then this one. Okay. And as this guy 0, so this is minus, minus, plus, and minus, so that would be minus here. Okay, and it's for this guy. Oh, here I have to put a positive sign here and sign here, because this is minus t0 over 2, so I have positive, right? But then this is the lower boundary, so I have to put another negative. A negative times negative is positive. Yeah, positive, and this one is positive. Okay, I got that. Now, you see that this one, omega 0 t0 over 2 is just pi. Okay, this is pi, and this is pi. But so I have 2x0 over t0 squared. The inside is minus t0 over j2k omega 0 e to the minus jk pi, plus this is also pi. Okay, plus 1 over k squared omega 0 squared e to the minus j k pi, and then minus 2 over k squared omega 0 squared plus t0 over j2k omega 0 e to the jk pi, and plus 1 over k squared omega 0 squared e to the j k pi. Am I in trouble? Now, okay, this is 2x0 over t0 squared. Inside is t0 over j2k omega 0, and that is j e to the j k pi minus e to the minus j k pi, and then plus 1 over k squared omega 0 squared e to the j k pi plus e to the minus j k pi, and minus 2 over k squared omega 0 squared. I think I'm in trouble. Let me see. Let me check this one again. Sorry, it's gonna take some time. Okay, so let's start with this. x0 over t0 over 2. So I got that. Okay, that is correct. This one, starting from minus t0 over 2 to 0, I have this. Okay, I have this. Alright, this one is here, and this one is there. Okay, the boundary is correct. Okay, t and t here. Alright, now I have to integrate it using well, I took this one out. So 2x0 over 2 t0 squared, and I move it to the right, and I move it across to the left. There, then I use by parts integral. Okay, and if I differentiate it, I'm gonna have, let me differentiate it back, e to the ax over a plus xe to the ax minus e to the ax over a. So these two cancel, so this one is right here, so that is correct. And then I have to integrate this one using this formula, the by parts integration. So a here, okay, a is minus j k omega 0. So I start with this one here. So minus jk omega 0, minus jk omega 0, and then t, and then e to the ax is right there, and then minus sign here, a squared. A is 1 over, a is minus jk omega 0, so this is a squared. Alright, minus sign is here. Alright, so this one is okay. And the other one, my minus sign is here, and then the integral is just exactly the same as the left one. So I'm gonna copy this over down here. Alright, and the boundary is here. Now I have to plug in all the boundaries. There are 4 boundaries. The first one is t0 over 2, so I plug in t0 over 2 here, and t as t0 over 2 here. Okay, so I have minus sign is here, All right, and then this one, plug in t0 over 2, so I have here, but then j squared is minus 1 and negative goes together. I've got positive, so k squared omega 0, and then t0 over 2 is here. All right, and then I have to, for the lower boundary, I have to put a negative sign, so negative times negative is positive. No, this one goes away, but this would have to be positive, right? But then I have j squared, so I have negative sign. When t equal to 0, this one is 1, so I have this. All right, that takes care of the first term. And the second term, when t is 0, this one goes away, and this one is 1, this one goes away, and then I have minus times minus is plus, but then j squared is minus, so minus here. And now the tricky one, the lower boundary. Okay, as for the lower boundary, I have to put the reverse sign here. When t is equal to minus t0 over 2, reverse the sign here, plus, and then it has to be plus as well because t is negative, so I have this term and this term, and then this one is plus, times minus is minus, but then I have j squared, so it's going to be plus again here, and then okay, it seems to be correct. And then I know that omega 0 t0 is 2 pi, so 2 pi over 2 is pi, so I have it right here, right here, right here, and right here. And now I'm grouping this and this together, so I take t0 over j2k omega 0 out, and then I have this guy subtracted by this guy. Okay, and the other one here and here added together. Okay, 1 over k squared omega 0 squared, and then I have this one. All right, now this one is 2 cosine of pi, right? And this one, no, sorry, this one is j2 sine of pi, okay, and this one is 2 cosine, k pi. This one is 2 cosine of k pi. Okay, but sine of k pi is 0. Okay, sine of k pi is 0. Now, as for cosine of k pi, depends on k. This is 2 when k is even, and minus 2 when k is odd. Because cos pi is minus 1, cos 2 pi is 1, so it is 2 when k is even, and minus 2 when k is odd. And so this term goes away, right? And this term will be 2 and minus 2 depending on the value of k. But when is this 2? Then this term will cancel, right? So it has to be minus 2. So we have 2x0 over t0 squared minus 4 over k squared omega 0 squared when k is odd. Let me check. Let me check the table for a second. Here. Here. Okay. When k is even, ck is 0. So it seems to be correct. And then 0 when k is even. Okay, so I have minus 8 x0 over k squared 2 pi squared. Now 2 pi, where does it come from? 2 pi comes from omega 0 times t0. That is exactly 2 pi. Now this is when k is odd, and it is equal to 0 when k is even. And I have 2 squared is 4, 8 over 4 is 2, so minus 2 x0 over k squared pi squared when k is odd, and it is equal to 0 when k is even. Now, so this is our ck. Alright, so the so see, I have all the ingredients because I have c0 equal to x0 over 2, and everything else is given by this, so I have ck equal to x0 over 2 when k is 0 minus 2x0 over k squared pi squared when k is odd, and 0 when k is even and not equal to 0. Now I have ck, so I can write down the Fourier series of x in the exponential form, complex exponential form. So that is x0 over 2 plus summation k goes from minus infinity to infinity, and k is odd, not equal to 0, and this has to be minus 2x0 over k squared pi squared e to the j k omega 0 t. So this is the Fourier series of the triangular wave in the complex exponential form. Now I'm gonna write it down in the cosine form. So x0 over 2, and then minus summation k goes from 1 to infinity, k is odd, and then I have this is ck, right? This is the magnitude of ck, so I have to multiply it by 2. So I have 4x0 over k squared pi squared, and then cosine of k omega 0 t. Oh, I have plus here because the face has to go with the negative sign, which is pi. So plus pi. Now the reason why the face is pi is because of the negative sign here. Okay, the magnitude is 2x0 over k squared pi squared, and that is the magnitude. This is the magnitude. The face is pi because it is a negative real number. Now this is the cosine form. This is the complex exponential form. Now I'm gonna plot the frequency spectrum of x. This is the magnitude. Okay, it's taken from this guy. So sorry. Uh, when k is 0, I have x 0 over 2. So I have this. This is x0 over 2, and for k equal to 1, I have 4 over pi squared, and that is 0.41. This is when omega equal to omega 0. It is 4x0 over pi squared. And the next one is even lower. This is 4x0 over, so I think this is x0 over pi squared, and so on. Okay, this is 2x0. Now we bring this, we plug in k equal to 1, 2, 3, and we evaluate the values and we plot it here. As for the phase is easy because the phase is pi for all k except at k equal to 0. So the phase is here and the rest would be pi. Now the reason why the phase is 0 when omega is equal to 0 is because this is positive number. This is a positive number, and positive numbers have 0 phase. So that's why we have 0 here. But the phase here for all k is pi, so that's why the rest has the phase of pi. This is the phase of ck, and that's it. So these are the magnitude spectrums. In other words, the magnitude spectrums taking the amplitude of each of the sinusoidal term, each of the cosine term, and plot them here, except for the first one. Okay, except for the first one, this is the first one, right? But the rest is just the amplitude of the cosine. All right, and that is the example. And actually, we have a table right here. We did this one, the triangular wave, and the results are exactly the same, coincides with the table. Minus 2x0 over pi k squared when k is odd. That's exactly the result that we have here. Okay, when k is odd. All right. Okay, so that is one example. So we've done a lot of examples to find ck. We did impulse train, we did rectangular wave signal, we did the square wave signals. Oh no, rectangular pulse train. I'm sorry. Let's start it over. We did 4 examples to find the Fourier series. First, the impulse train. Second, the square wave. Third, a triangular pulse train. And fourth, the triangular wave. Okay? You can do a lot more, right? You could do the sawtooth. Sawtooth is right here. Have we done sawtooth yet? I don't think we have. Okay, sawtooth is right here. You could do this one. You could do this one. This one is rather tricky. I don't think you should do it. But this one is not so difficult. You should be able to do this one. Okay, we have done this one, we've done this one, we've done this one. I'm sorry, this one we haven't done. We have done this one, we've done this one, we've done this one, we've done this one. So we are left with the sawtooth, we're left with full wave, we are left with the half wave. But we don't have time to do all of them, alright? Okay, I might go back to do the sawtooth for you guys, but right now I have to move on. Okay. So the next topic would be the properties of Fourier series. The first property is called linearity. Suppose you have two signals x and t. Both of them have the same period. Okay, and the period for both of them is t0. And suppose we know the Fourier series of x and y. The Fourier series coefficient of x is ak. The Fourier series coefficient of y is bk. And then we add them together. We do the linear combination between x and y. Okay? And we call the linear combination as z. Now, it turns out the Fourier series coefficient of z, which is called ck, is just the linear combination, the same linear combination of ak and bk. Alpha here is the same, and beta here is the same. Okay, so when you add two signals together, then the Fourier series coefficient of the result will be the Fourier series coefficients of each of the terms added together. So in other words, ck of z is the same linear combination between ak and bk. Okay? Alright. For example, if I have this one, if I have this signal, okay, it seems rather complicated, but it is not actually. And so on. Here. Now, if I want to find the Fourier series of this signal, what do I do? This is zk, zt. Now, if you notice, this is actually these two added together. Okay, I'm gonna do this and then I'll put it here, and then I put it, sorry, here. Let me okay, I have this. I have this. Okay, and then this, this. Oh, I have this. See that this the top signal Z is equal to this signal added by this guy. Okay, but the low one should be here. See, if you add these two signals together, if you add this and this together, the result will be this one. Okay, can you see? Here we have the first part, right? The first part is this part. Okay, this part. You add this one with this one. Okay, see this one, right? And on top of this one, you have here. So this one, this part, this section is this one, all right? And this section on top is this one. So you add them together, you're gonna get this one. Now let's call this one x of t. Let's call this x of t, and let's call this y of t. So we see that z of t is equal to x of t plus y of t. Now somehow, if you could find the Fourier series coefficient of x and Fourier series coefficient of y, so if we know so if the Fourier series coefficient of x is ak and of y is bk, then the Fourier series coefficient of z will be ak plus bk. Okay, that is convenient, right? Now, the question is, how do we find the free series? How do we find AK and BK? This is for AK and this is for BK. Now, how do we find them? Here, you see, XT is XT looks like a triangular pulse signal. YT also a triangular pulse signal. Sorry, except that XT is the time shift version of the rectangular pulse signal. YT is also a time shift version of the rectangular pulse signal. So I think we could easily find AK and BK. Now, once AK and BK are found, we can find the CK for the signal Z quite easily by adding A and B together without having to do the integration for ZK, because that would be complicated. So this is the use of linearity, and I think it's very useful. Okay. And the second property is time shift. Remember here, this looks like a rectangular pulse signal, except that it is time shifted because rectangular pulse signal is an even function. This is rectangular pulse signal. So you time shift it to the right by half t, you're gonna get xt, right? And to find the Fourier series coefficient of a time shifted signal, it's quite easy. Okay, here y is xt time shifted to the right by t0. So what we do is the Fourier series coefficient of y called dk is just the Fourier series coefficient of x called zk multiplied by complex exponential e to the minus jk omega 0 t0 here is the amount of time to be shifted. Okay, and that's quite easy, just multiplied by this factor and you're gonna get the Fourier series coefficient of y. Convenient. For example, okay, consider the shifted rectangular pulse train, this guy. Okay, if x is a, let me go here, rectangular pulse train, where is that? Here, this is the rectangular pulse train. Let's copy it and bring it down there. Here, this is the rectangular pulse train. Okay, see, this is the rectangular pulse train. This is the usual rectangular pulse train. Do you see they resemble, right? They're resemble to each other. And y is just x shifted to the right by well, actually, where did this come from? Let me make a correction. Okay, this has to be t, oh sorry, this has to be t over 2 minus t over 2, and this is t0 minus t0. Okay, this is 2t0 minus 2t0. Right here, erase this. And then this is t, this is t0, this is minus t0 minus t0 plus t. Okay, now you see y, if you shift x to the right by t over 2, if you shift x to the right by t over 2, right, you're gonna get y. Look at this pulse. Look at this pulse. The pulse at the top is the pulse at the bottom shifted to the right by t over 2. So I can write down y as x in parentheses t minus capital T over 2. All right? Because y is x shifted to the right by time t over 2. Okay, and because we know the Fourier series coefficient of x, because this is a usual rectangular pulse train, and we know from the table we found it actually to be this. So because y is the shifted version of x, we know that Fourier series coefficient of y is just ck multiplied by this complex exponential, and this is the amount of time we've shifted, t over 2. This is t over 2. Okay, this is the shifting the time that we've shifted. All right, so this is just the Fourier series coefficient of y. Okay, quite easy, right? You don't have to do the integration again. If you know this one, if you know the Fourier series coefficient of this one, and you know the relationship between x and y, then you can find, then you can find the Fourier series coefficient of y quite easily. And as for amplitude transformation, okay, if y is alpha x plus beta, alpha and beta are constant, then the Fourier series coefficient of y when k is 0 is just the linear combination here. Same here, right? Alpha and beta are the same, except that you plug in z0. If you want to find d0, you plug in c0. But except for k0 other than k equal to 0, when k is not equal to 0, dk, which is the Fourier series coefficient of y, is just alpha ck. You don't have to add beta in. Beta will be gone, okay, if k is not equal to 0. For example, I'm going to give you an example here. Okay, now let's do this example. X here is a sawtooth signal. Now we know the Fourier series coefficient of x. Let me go to this table. Now for sawtooth signal, the second one, the Fourier series coefficient is this. So let me copy it and bring it down here. Okay. This is the Fourier series coefficient of sawtooth. This is ck. When k is not equal to 0, this is c0. Now, we want to find the Fourier series coefficient of this signal. How do we do that? We have to be vigilant, and we have to notice that y here is just the reciprocal of x. You see, if I want to plot, so you see, the height of y is 4, and the height of x is x0. Okay, so somehow we have to scale the amplitude of x by a factor of 4 times x over 0. So 4 over x0 times xt. If I do this, then I'm scaling this one. Okay, Then I'm scaling this one. But you see, they go against each other. One is increasing, the other one is decreasing. So we know that the sign here has to be negative. Okay, the sign here has to be negative because you see they are mirror image to each other, right? So we have negative sign here, and the scaling, okay, go from x0 to 4. So we have to multiply x by 4 over x0. But then this signal, what is this signal? If you plot this signal, you're gonna wind up with this. Right? And then this is 0. This is minus 4. Okay. If you plot this one, you're gonna get this. Right? The amplitude of x is x0, and the amplitude of this guy is minus 4. Okay? But what we want is this one, so we know that we have to shift it up 1 unit, right? We have to shift it up 1 unit. So we know we need to shift it up. To shift up, we add it. Since we need to shift it up 1 unit to get y, it follows that y is minus 4 over x0 times the signal xt plus 1. Hence this equation. So now we have found the algebraic relationship between x and y. X here, y here, so y is minus 4 over x0 plus 1. Now we could use this property. Alpha is minus 4 over x0 and beta is 1. Yeah. See, got this one. Alpha. This is alpha. This is beta. Okay, as in the previous property. So we know that d0 here is just alpha z0 plus beta. But for the rest, everything else dk, you don't have to add beta, and you're gonna get this one. But then I have to plug in the sawtooth, right? From the sawtooth, c0 is x over 2, and ck is jx0 over 2 pi k. So plug in c0 as x over 2, and the rest is jx0 over 2 pi k. That is for xt. So for yt, dk, so c0 plugged in here, I've got minus 1. Is that right? Yeah, I've got... I think it should be minus 2, isn't it? Minus 2. This is not correct. It should be minus 2. Minus 2. And this is and, not and plug in this guy to here. I've got this one. This is correct. Okay, so this is the Fourier series coefficient of y. That's it. Okay, you don't have to do the integration again, because the integration of this one, if you want to find the Fourier series coefficient of this signal directly, it would be very messy, a lot messier than this one. So we don't do that. Okay, we use a shortcut by finding the relationship. The key thing here is to find the relationship between this guy and this guy. Once we have found the relation between them, we could use that property because we already know the Fourier series coefficient of this guy, right? So we could use this property, okay, to find the Fourier series coefficient of y quite easily. As for the time reversal, okay, we flip it around 180 degrees. If we flip a signal around 180 degrees, the Fourier series coefficient would have to be complex conjugate. Okay, a star means complex conjugate. Okay, for example, as for time scaling doesn't change the Fourier series coefficient. So time scaling, Fourier series coefficient are invariant to time scaling. Okay, now let's do example. We know the sawtooth signal, right? The sawtooth signal is this. Okay, if I do the time reversal, I have this is a time reversal. Okay, this is xt and this is yt. So we see that yt is x of minus t. Okay, but the Fourier series coefficient of xt are c0 equal to x0 over 2. This is x0. Okay, and ck equal to what? J x0 over 2 pi k. When k is not equal to 0. So the Fourier series coefficient of yt are, okay, c0 is just c0 because it is a real number. You take conjugate, you got the same result. And but for ck, well, let's denote it by d0. It's just ck conjugate, right? Conjugate means that you put the negative sign, you switch the sign of j, so it is equal to minus j x0 over 2 pi k when k is not equal to 0. Okay, so this is the Fourier series coefficient of this guy, because we know y is a time reversal of x. So the Fourier series coefficient of y is just the complex conjugate of the Fourier series coefficient of x. So we got this one. Once we know ck, we can easily find dk by taking conjugate of ck. Okay, so that concludes our Fourier series chapter. Okay, and I would like to remind you that we won't have class on Tuesday, and we'll meet again on Thursday. And on Thursday, I'm gonna begin another chapter, and that is Fourier transform. That is first thing. The second thing is, I think we have an appointment. The short exam is coming up, and the short exam is on Friday. Okay. Reminder.
อาจารย์ครับ
Yeah.
วันศุกร์ผมมีไปแข่งฟุตบอลครับก็จะมาสอบไม่ได้
Wow.
ตั้งแต่ผมไปตั้งแต่วันพฤหัสที่28มาสอบอยู่ครับ
Okay. All right. All right. Send me an email. No class on Tuesday. Okay. Short exam on Laplace transform on Friday. Friday 29th of March. Time is 15 o'clock to 16 o'clock. And the room is, I've got the room already, 17401. Okay, this is the reminder. Those who could not take the short exam, please contact me later and we take it later. Okay? Any questions, please? No? All right. Thank you for joining the class today and appreciate it. And see you next Tuesday. I'm sorry. See you next Thursday.
อาจารย์ครับอันนี้อัดไว้ครับโอ้เนี่ย
Sorry? Say it again.
อันที่อาจารย์สอนวันนี้อาจารย์ได้อัดไว้ไหมครับ
Yeah. Okay. All right. So if there are no more questions, see you next Thursday. Bye bye. Have a good weekend.